So what do we do as a modeler? What do we want to see? Modeling itself actually does not show you anything. It's just nothing. It is not crystal ball. In many cases, as modeler, I got questions like, can you model this or can you model that? Sometimes we don't have assumption, but can you get this result? My answer is going to be always the same. Yes, I can do it, but for what? So what do you want to do and what do you want to see? What knowledge do you have? And based on what kind of assumptions you want to get the result? That's the question. So modeling is not actually a crystal ball. It doesn't predict anything. It actually organizes the knowledge and the data you already have inside of you, and then bring it out as a structured format. So modeling, a good model represents your perspective and your knowledge and your data. So modeling is more likely pensive. Are there any Harry Potter fans here? Harry Potter fans, thumbs up. Actually, I love Harry Potter. And yeah, personally, I don't like the author too much, but I like the story itself. So it is more like a pensive. So if you watch the Harry Potter, you know what the pensive is, right? Using the magic wand, you can get your like memory and then put it into some sort of big ball. And if you put your face in the ball, you can see your past. So that is actually the modeling. So modeling helps you to get your own knowledge out to the real world. So a good model will represent what you want to see in many cases, if not always. And a good model is based on your knowledge, and a good model is based on scientific evidence and historical data. What we actually do is understanding how things will be revealed based on our knowledge and our data and our scientific mechanism. It helps organize, project, and explore our thought and knowledge. So I'm stressing this out a lot because modeling is not something from the universe or outside of the world or something. It is actually from inside of the modeler. So if we have everything, what is the point of doing the modeling at all? We already know what the model will show almost always. We already know what we want to see almost always as well. Then what we do need, why do we need the model in the first place? Because we don't build models to see the future. I mean, sometimes we can project the future. I mean, many times we project futures using the model, but it's not the point. The point is that we build the model to understand how the future might unfold and how our actions will shape the future based on our assumption. So the key is the assumption. And the model helps us to find the strategic pathway based on our assumption and the data. And it helps us to find setting goals, prototyping, and implementing and evaluating. So those are the process. The entire process is actually the modeling. Just programming is a part of model. And usually modeler says programming is only 10% of the entire modeling process, less than 10%. It's not the key. The key is designing the entire process. That's the key. So model will definitely help us to ask correct questions. That is very important. In many cases, we have knowledge, but they are pretty messy. So how many of you actually can get an idea how one policy can affect to reduce greenhouse gas emissions very clearly in 1 or 2 sentences in 10 minutes or something? Sometimes it is, I mean, because you have much more knowledge than almost everyone else in climate change and energy sectors, sometimes it is more difficult than anyone else because you understand it is complex. So a model definitely helps simplify and structure the complexity so we can reason clearly. Just like pensive, let Dumbledore view memories more objectively. So models allow us to be more objective. So model helps us to connect knowledge, data, and logic. So a good model acts as a bridge between what we know, which is theory or experience, and what we have seen, which is historical data, and what we think something will happen, which is assumption. And the last is what we want to ask, is a scenario and prediction. Those are very important key terms that we must understand. That's why, although I'm a modeler, when I model, when I do the modeling on energy side or maybe hydrogen, I can do it myself because I have long experience in hydrogen and energy sector. But when I do a modeling on shipping or steel sector, usually I rely on the shipping sector experts because if I don't rely on their own knowledge, what I build is just nothing. It's just calculating numbers based on something very unuseful knowledge. So it will not make any sense. So model itself is a way to communicate in many cases to explore. Model helps us to explore what if questions, and it allows us to make proper decisions. We can't actually run experiment on the real world easily like Trump is doing at the moment. Like if you put import tariff to China, what is going to happen? If you don't do the modeling, the only way to the experiment is actually increase the tariff and put a tariff. However, if that happens, you can't bring it back. Even if you bring it back, you can't go back to the previous status, right? Right? Everything's already changes. It's immutable. So we can't test the scenario in the real world. That's why we use models to test the scenarios. And we want to understand the risk based on very different scenarios. And we want to optimize our choices. That's the reason why we use models. Another is it actually exposes hidden assumption because modeling forces us to make our logic explicit. It actually forces us to think more deeply on the relationship between interactions between agents. And it means it questioning our assumptions. We need to question our assumptions if that's correct, if it's not. We need to identify what matters the most. And we need to improve collective understanding as well. And modeling is a way to share the idea with other people. Even if you have a very good idea, if you don't write it down, there is no way you can bring it out of your brain, right, out of your mind. So modeling is basically the same. As modelers, we use models to communicate with others. For example, when I talk to Jinsu, when we do the modeling, definitely we talk through the phone or face to face, but the easiest way is share my code with Jinsu or Jinsu shares his code with me so that we can understand what is the logic behind and what is the problem to fix. That's the way that we communicate. So again, models are objective, not always very objective because but modelers are subjective. So then models actually help modelers to be objective. So the component that need to be objective is assumptions. Assumption is some sort of subjective. However, being more stated very clearly and making assumptions justifiable and transparent, we can make assumptions more objective. And the structure, if our model is based on scientific mechanism, physical laws, and logical reasoning, the structure of the model and way of thinking becomes more objective. And then data input. Data also need to be very objective because number is just there, data is there. Why it can't be objective? Because if you cherry pick the data, it becomes subjective. So you should use all the data as possible. And then when you choose a certain data, you need to have a very clear rationale why you choose the data. Subjective decisions we must recognize include which variables to include or leave out, or how to frame the problem, what resolution or scope the model, or which scenarios to explore. And after all of this thinking process, we need to make sure, we need to validate the process comparing with real world observation or known behavior. One way is, for example, in case of uh, carbon budget calculation. After you calculate the carbon budget, one way that you can validate is comparing it with the historical data set. So we can calculate carbon budget using the historical data by 2020, and then calculate the carbon budget of 2021 and 22 and 23. Then we can compare it with actual output of 2021 to 3. Using that approach, we can validate if our result or if our works is good or wrong. Another is that models can be biased by your own knowledge and your own position. The one example is energy transition model. Objective part is physics-based wind, solar output, grid flow equations. They are all objective, but choosing which regions get renewable first and what kind of policy will be included, they are subjective. So mixture of objective and subjective is very important. The same for economic. Economic model is known for very objective. However, it is still there is subjective part, for example, of behavior and future interest rate, inflation target. So you can set interest rate to be 2% or 3% or 4%, and discount rate, different discount rate, they will actually distort the result quite a lot. And same for climate impact model. Although we have clear idea how this greenhouse gas emissions will affect our life, but societal vulnerability level, adaptation strategies, and discount rate actually can distort the result. So there is subjective component. Why am I telling you about this objective and subjective quite a lot? Is because there is very, very, very important sentence that I always remember. Two important sentences as modeler. One is modeling is half science and half art. So it means half objective and half subjective. Another one, very important, is garbage in, garbage out, or rubbish in, rubbish out. So yeah, even if your model is very objective, it doesn't matter. If you put garbage into your model, what you get is just garbage. You can't use it. It's like a chef cooking nice food using food rubbish or food garbage. In the end, it might look great, but you can't eat it because it's already garbage or rubbish, right? So that's very important. So to avoid the situation, garbage actually does not only about data, but also about assumptions, scenarios, and wrong understanding of the specific sector that you are modeling. So yeah, how can you avoid? To avoid it, we need to always ask, where did this assumption come from? Are they actually tested? And are they validated? And after you make the model, are we actually communicating with this data and output correctly? Or more directly, we can say, are we actually communicating frankly? So if we find something that doesn't match with our perspective or our messaging way, it is time to change our message rather than change the result, right? So we need to deal with those, we need to make a balance between these two. So modeling is all about assumption. It's just all about assumptions. So far, I think I used word assumption more than 100 already. It's all about assumption. Based on assumption, what kind of result you get. So modelers should not say the model says X will happen, because modeling is not crystal ball. But you can say if A, B, and C hold true, then X is likely outcome. So that's based on this kind of assumption. This is the outcome that we expect. So models don't predict, they condition. They show what follows logically and scientifically if your assumptions are true. Very important. If your assumptions are true. If your assumption is wrong, then everything's wrong. So the real power of modeling is not seeing giving you a single number or great numbers. It is about connecting assumptions to mechanisms and to consequences. So it is all about the relationship. So this result actually, the result of this model means nothing without its foundation. It is you can't just get the cherry on the cake. You need to have entire cake, and you need to publish how inside of the cake as well to make sure these assumption and models are correct and not biased. So assumption, for example, assumption can be demand will triple by 2040. And if the model output is massive investment in capacity is needed or infrastructure capacity is needed, the lesson we get here is the conclusion depends entirely on demand assumption. If we forget about this demand will triple by 2040, then model output means nothing, because if the demand doesn't increase, why do we need to invest more in our infrastructure capacity, right? So it's all about the assumption. So what you always need to say is what you always need to remember is you should not present a result in isolation, means without assumption. Under these assumptions, this is what emerges. Therefore, we should prepare for this possibility. That's how you need to write when you use a modeling result. So to be more responsible, need to ask, what are we assuming? Why do we believe this? And what happens if it doesn't hold? And always, again, assumption need to be presented side by side with the result. So assumption and result. And that's why modelers actually love scenarios, multiple scenarios, and even sensitivity analysis. For example, when you see those climate models, you can see the variation. For example, when we see the carbon budget calculation, sometimes it says there is a 50% of a chance that 1.5 degrees Celsius can be met, right? The target can be met, right? This 50% means from this 50% comes from the sensitivity analysis. More than 1,000 models are included in the analysis and then get 50% of a chance. So we definitely need that in mind. So doing the modeling, I'm explaining these things a little fast because I want to do a bit of a workshop on Google. So the goal, what we actually do as a modeler is not make every single model's perfect prediction. We can't really predict anything, and we can't be perfect. But there is very important things. First, we must be transparent. We need to write all the assumptions and sources on a document or report. And we need to clearly distinguish what is assumed and known and estimated. And second, need to be very systematic. There are lots of tools that help you to be systematic. And one of the tools that you can use is GitHub. And you need to apply, but in general, as a framework, you need to apply the same logic to all scenarios. If you apply one logic A to scenario A and logic B to scenario 2, those two are totally different. It's not comparable at all. You are comparing apple to oranges, so you can't do that. So always need to be apple to apple comparison. And third, this is the most important and most difficult part. When you model it, you need to validate and cross-check it. So when you have a task to model something, let's say the project period is 6 months, you need to finish the job within 3 months, just a half, because validation takes another half. Validation always takes longer than actual coding process and modeling process. And also need to invite a peer reviewer or external criticize. You need to be happy about being criticized. Don't need to worry about it because it's a very healthy process. There was very unfortunate incident about 5 years ago. A professor in the United States actually sued other professors because they criticized his paper, and took about 2.5 years until he finally um, give up, giving up on progressing the lawsuit at all. But as a academia or as a modeler, getting criticism is more likely getting interest, like a thumbs up from other modelers. If they don't have interest in your model, they will just ignore it, not really try to see it. So need to be happy or not. I mean, it's not happy. Always being getting criticism is not happy, but you need to be open to the criticism to be a better modeler. And yeah, the last one is stay humble. It's from Steve Jobs' talk about 20 years ago. Need to stay humble. Models are just tools. It doesn't show you the truth. So don't rely on the result of the model too much unless you present assumptions as well. So next is I want to explain this model. Are there any people who actually seen this result or heard of this, the limit to growth? Can you thumbs up, right? This is super famous model, right? The limit to growth done by the Club of Rome. For those who never heard of this, you may want to check on Wikipedia. Already Wikipedia, I don't rely on Wikipedia too much, but in this case, Wikipedia explained quite well. So this is a system dynamics model. If current growth, this is what it explains. If current growth trend in population, industrialization, pollution, and resource use continues and unchecked, the planet will reach its ecological resource limit, potentially leading to the population degrowth. That's what this entire model explains. However, it didn't happen, right? This model is built in, if I remember correctly, is it 1970 something? I think 1970 or 1975, somewhere between. Was very first system dynamics model, but this actually didn't happen. It is expected by 2020, all the population will peak and then reduces and everything will decline and then the entire economy will collapse, but didn't happen. Why? Because it did not understand, it did not include fully anticipate technological progress, and it assumed the limited adaptability of a human being, and also it used a very simplified model. So is this model wrong? Can we say it's wrong? Hmm? No, actually, we can't say it's wrong, actually, because this model did its job. What the Club of Rome actually wanted to say was the entire world will collapse. What they actually wanted us to say was they wanted to warn the people that there is a chance that we will collapse, so we need to prepare. So this model actually did its own job. So basically this model is based on IPAT equation, which is pretty famous as well. I is impact, and P is population, A is affluence, T is technology. So IPAT is I equals P multiplied by A multiplied by T. So population increase and affluence increase and technological increase will increase the impact. That's what it says. So this is very interesting one.